Alright, so today we're going to explore the cornerstone of mechanics, which is the Newton's laws of motion. So I'm sure that all of you are at least somewhat familiar with the concept of forces. I suppose you like to think of forces as a push or a pull. What Newton's laws do for you is that they formalize the concept of a force. Newton's laws give us a solid idea of what exactly a force is and what it does. So to summarize the content of Newton's laws, this is what we know. We know that first of all, a force is a vector quantity that changes the velocity of a massive object. It's important to understand that for an object to have or maintain a velocity, you don't need a force. You need a force only to change the velocity of a massive object. The second important property is that forces never occur alone, but in the real world, forces always occur in pairs. That's captured in Newton's third law. So let's look at all of this in detail. So what's Newton's first law of motion? Newton's first law of motion concerns an isolated object. What's an isolated object? A good example of an isolated object is one that's just floating in space. It's got no forces acting on it. There's nothing anywhere in sight that's providing any push or pull or interacting with this object in any way. Okay? So our idea of an isolated object is one on which no forces act. And Newton's first law says that such an isolated object will have a constant velocity. By constant velocity, we mean that it will either move in a straight line, or if it's stationary, it will remain stationary. So this isolated object could stay like this forever, or it could move in a straight line onwards and onwards without changing either the magnitude or direction of its velocity, right? So Newton's first law tells us that when there are no forces acting on an object, the velocity of the object does not change. Another way to think of Newton's first law is the following. If you're given an isolated object, you can always find a frame of reference where that isolated object has a constant velocity. This leads us to an alternative statement of Newton's first law that is sometimes found in literature. So you might often see this statement, which is that Newton's first law states that inertial frames of reference exist. We will look into these inertial frames of reference in more detail later. For now, let's just understand that Newton's first law says that isolated objects move with constant velocity, and that constant velocity could even be zero. Okay, alright, now let's look at Newton's second law. Newton's second law concerns objects which are not isolated. So once again, let's think of a point mass m. This time the point mass m is not isolated, but there's a real physical interaction happening on this mass. Somebody or something is pushing or pulling this object, and we like to capture that information in something called a free body force diagram. So we have, let's say, a resultant or unbalanced force acting on this mass given by this arrow. So there's a resultant force acting on this direction. What Newton's law tells us is that this force causes the mass to accelerate or change its velocity according to the following equation: F equal to ma. So a couple of interesting things to note here. First of all, this is a vector equation. What we got here is that if you have a force of F acting on the mass m, you will get an acceleration vector for the mass. This acceleration vector, of course, points in the same direction as F, but it's scaled up or scaled down by a factor of m, right? So we have a equal to F by m. What that means is that the velocity vector of this point mass m will change with time because of this unbalanced force acting on it, okay? Really, the velocity vector will change. It's not sufficient to say perhaps that the speed will change or something. The velocity vector is going to change with time because of this force. And another very important point is that this equation we wrote down, F equal to ma, is not the general form of Newton's second law. This is the special form that we like to write down for point masses. The general form of Newton's second law goes like this. So the general form is F equal to dP by dt, where P is defined to be this quantity. Do you know what this quantity is called? This quantity is called momentum. So P equal to mv is the momentum of this body. So of course you notice that for a point mass m, which when the mass does not change with time, we get, for m constant, we have F equal to d by dt, right? And we will have P here, right? But then P is mv. We can pull m out of the differentiation if it's constant, and we will recover the special case that we wrote down. But in general, the Newton's second law is given by F equal to dP by dt. This is especially important if we deal with cases where, you know, the mass doesn't stay constant. For example, very classically, when we want to deal with rockets or something, which, you know, change mass because they eject fuel, it will perhaps not be sufficient to deal with those situations using just F equal to ma. All right. So once again, this is a special case for constant mass. And the general statement of Newton's second law is that an unbalanced force on an object changes the momentum vector of that object. Now let's look at Newton's third law of motion. Newton's third law of motion really captures two things. First of all, it captures the fact that forces are the result of real physical interactions, right? If you have a force on some object or point particle, you know, that force doesn't come from nowhere. It must be that some other particle or some other external agent or object is responsible for providing the force, right? And the other thing that Newton's third law captures is that forces always occur in pairs. So let's look at these things by considering 2 point particles. Let's say we have particle 1 and particle 2. Now let's say the force due to particle 1 on particle 2 is like this. So particle 2 feels a resultant force, and that force is due to this object 1, right? The force didn't come out of nowhere. Particle 1 is responsible for providing this force on particle 2 somehow, right? And the force is given by, let's say, F1, 2. In this notation, what we try to mean is that the force due to 1 on 2. What Newton's third law says is that in this scenario, the particle 1 is also going to feel a force. It's going to look like this, F, and this force is due to the particle 2. So that we could write that down like this. It would be F21, which is the force on particle 1 due to particle 2. What Newton's third law then says is that these two forces are a third law pair. They're exactly equal in magnitude but opposite in direction. Or in other words, F21 equal to minus F12. It will always be that if you have a force acting on some object, there must be an equal and opposite force on whoever is the agent providing the force on that object. All right? So for now, we've presented the statement and the content of all three of Newton's laws of motion.